1.2 of the Groundwater Management Model tutorial series. In this episode, we'll look at components of the management model. How do you actually build a management model? And we'll look at some constraints that are possible on head and stress rates, and then some examples of constructing a formulation using those constraints. So let's first look at the components of the management model. And there are three of them: decision variables, objective function, and constraints. The decision variables are those variables that you are, as the name implies, trying to make a decision about. In most of the examples, we'll look at the flows at sets of cells during specified stress periods are the decision variables. For example, pumping rates at a cell in a stress period or over multiple stress periods will be the decision variable or decision variables. The objective function is a function of the decision variables and state variables. It is either maximized or minimized, and as we'll see, it typically has some sort of economic interpretation, although there are exceptions to that. And finally, we have constraints, which are limits on the values of the decision or state variables, or controls on the relationships between those entities. So just as the simulation model has a solver that solves the system of linear equations that are produced, a numerical solver, the optimization formulation, the management model, has an optimization algorithm that solves the problem and finds the set of decision variable values that optimize the objective while satisfying those constraints. And we'll see all that in later episodes. So first we'll look at a simple constraint, head upper bound. So the notation works as follows. Here is the set of pumping rates. These are the decision variables. Withdrawal or recharge rates. We use them to compute a head at a location. In this cartoon, this is this location A. And the constraint is that we require that head, as we change stress rates, be less than or equal to a maximum value. So for example, if we were recharging at this location, producing a mound, we might want to be sure that the head at this location, A, does not exceed this maximum value. And let's look at an example now of where that might come into play. So this is a construction dewatering problem. Here's a construction excavation that is to be carried out. The existing water table is indicated by the dashed line, and dewatering will be necessary, and we're going to accomplish that by pumping at certain rates at these 4 wells. So that's the problem. We want to accomplish that with the minimum amount of pumping. So first let's look at the constraints. We're going to select 5 locations, which are indicated here, 1, 2, 3, 4, 5, and require at each of those locations, here indicated by the subscript, that the head be less than or equal to an upper limit. So the water table or the piezometric surface must drop below these indicated levels at each of those points. And again, as a reminder, the QW is a vector representing the 4 pumping rates at the 4 wells. So the head at each of these locations as a function of those pumping rates has to be less than or equal to these upper bounds. One might imagine that there are many possible ways to do that, many combinations of pumping rates that could be used to accomplish that. We want to select one, and in order to do that, we define an objective function. And in this case, which is a steady state case, by the way, we will select as our solution that which minimizes the sum of pumping rates as indicated by this function. So we're simply adding up the pumping rates at the 4 locations and making it as small as possible. So here's our complete formulation. We're minimizing, here's our objective function, we're minimizing the sum of pumping, and here is our set of constraints, and those must be satisfied. And here, of course, are our decision variables. Now, I just want to mention this question, will this yield the optimal solution? Of course, if we put this into an optimization algorithm and solve it, yes, it will. However, it's of course no better than our simulation model and the specification of constraints and objectives and candidate well locations. So these elements of the problem are important for finding an effective solution. One other thing to mention here is the notion of candidate locations for wells and those wells actually selected. In the problem we just examined, there were 4 candidate well locations, and it may well be that only 2 or 3 of them are selected for pumping. In other words, the pumping rates for 1 or 2 of those 4 would be identified as 0 by the optimization algorithm. As we'll see in future episodes, there are other ways to handle well selection, location selection, but this is a very simple one. The next type of constraint that we'll examine is the head lower bound. And here we have a drawdown situation, so we might be requiring that the head at this location A be no lower than a minimum value. And let's look at a formulation or a situation where that might come into play. This is a subsidence control problem. So the problem here is that we would like to withdraw as much water as possible from these 4 wells, but we want to avoid subsidence beneath the building, which we're going to simulate or represent as maintaining water levels above a certain elevation. So we'll select 3 locations, 3 control points, 1, 2, 3, and require that the heads at those control points be greater than a lower bound. Those are our constraints. Now, what's a little different about this problem is that it is transient, so now we have T stress periods, and that applies both to the constraints, which are imposed in each stress period, and also to the decision variables, where I have the potential for a different pumping rate in each stress period. So for example, if this is a 1-year period and I have monthly stress periods over a year, 12 stress periods, then I would have 4 times 12, 48 decision variables, and 3 times 12, 36 constraints on the problem. We need an objective again, and in this case we're going to maximize the total pumping over all 4 wells and over all stress periods. So here's the complete formulation. Once again, the decision variables are now pumping rates at locations and stress periods, and constraints, and an objective function. One other type of constraint that's worth mentioning at this juncture is bounds on flow rates. So we may have individual flow rate bounds, upper bounds on pumping rates, withdrawal rates, and we may have bounds on groups of rates. For example, if this is a water supply situation, we might have a minimum demand that must be met by the summation of pumping rates, or a maximum that cannot be exceeded. And using that, I want to show an alternate formulation for this same problem. So let's study this one. I'm going to assume the setup is this. We are required to withdraw a certain amount of water, Qt, in each stress period, and that is going to be the sum of the 4 pumping rates in that stress period. That's now a constraint. And we would like to avoid excess subsidence, but we're going to accomplish that by simply maximizing the sum of the heads, which is an indirect way of saying we'll try to keep the heads as high as possible while meeting the demand for water. It's a different problem, different way to formulate this would yield a different solution. And how about this one? This is yet another way to formulate this problem, and that is to use something called the maxi-min formulation. We define a variable r whose value is undefined, but is held to be the bound on the heads at each location and in each stress period. So all heads must be greater than this value r, and we will attempt to maximize this value r. In other words, we're maximizing the minimum head over all locations, all 3 locations, and all stress periods. And we're doing this, in this case, while at the same time that we're meeting the demand for water supply. So yet another formulation that one can use for the same problem. We'll look at some additional constraints and additional formulations in the next episode.